Hello and welcome. In this diesel cycle problem, the compression ratio, volumetric compression ratio is given. However, the cylinder displacement is provided to us instead of the volume at the bottom dead center. So we have to use the definition of the compression ratio to figure out what is the volume at state 1. Also, the maximum temperature is not supplied. So to find state 3, which is the same pressure as state 2, we need one more condition that comes from the heat addition. Q in is given to us, so we can use the energy equation. Q in is m times H3 minus H2, and so that will give us an equation for H3 as H2 plus Q in over m. So that's what we are going to use in state 3. So let's first quickly go over an animation to show you the connection between the compression ratio and the volume at the bottom dead center and clearance volume. These are simple geometric equations. So we will translate this equation into the I/O panel and declare suitable variables. The appropriate test step to learn should be we follow the specific closed branch, the green branch, and IC engines is right here, and the IG model would be our model in this problem because we've been asked to use the IG model. Specific heats are function of temperature now. So I've already solved the problem for the sake of time, and I'll just walk you through my solution here. So first let me show you the variables I have declared in the I/O panel. The compression ratio is the obvious one. First of all, it's given to us as 20. And then the volume, the D, by that I mean displacement volume, that's in meter cube instead of liter, is given in liter, and then clearance volume can be obtained from the definition of compression ratio, and therefore the volume at bottom dead center is found. This is what we are going to use at state 1, and just for the sake of it, our check should be same as 20 because it's from the basic definition, just to make sure we didn't make a mistake. And then we can find cutoff ratio from volume, state 3 by state 2 volume ratio, and Q in is given to us, and this is the enthalpy equation that I talked about we are going to use for state 3. So first thing first, as you click the calculate, of course we already solved. You can see our check should be 20 just like we anticipated, so we didn't make any mistake in our equations. Finding the states for state 1, let's start with state 1. Pressure is given to us, and volume is volume at the bottom dead center. It's not the displacement volume, it's displacement plus the clearance volume. So knowing the temperature, pressure, and the volume, we can find the complete state. State 1 is completely calculated. For state 2, which is an isentropic state, S2 must be equal to S1, and the volume is divided by the compression ratio R, as you can see. And of course, the mass remains constant, and that allows us to find state 2 completely. State 3, again, would be constant pressure heat addition. That's how the diesel cycle operates. So pressure remains constant. And instead of temperature, the enthalpy now is known from the energy equation. Instead of writing the equation here, we have written enthalpy 3 in the I/O panel. Notice that in the I/O panel, we couldn't use a variable called H3 because H3 is reserved for state 3. That's why we had to use a long name or something else. Okay, so state 3 is found, and state 4 would be isentropic to state 3. So that's S4 must be equals S3, and the cycle is complete. So volume 4 must be equal to volume 1, and of course mass is constant. So now that we have found all our states, in the graphics panel, we should recognize that through state 1, constant volume line should pass through 1 and 4. And if I want to draw through state 2, it will be constant pressure line connecting 2 and 3. A constant volume line would not go through 2 and 3, as you can see. And constant volume line, as you can see, is steeper than the constant pressure line, as we all know. Okay, so now that the states have been correctly calculated, in the process panel, essentially all we do is just put those together. We go from state 1 to 2 is the compression. If we do we should be putting heat transfer to be 0 because to find a more precise value of work transfer. So the boundary work which is external work, is found for for process 1. For process 2, if you just click calculate, it will calculate everything, because we already know boundary work can be found from the constant pressure condition, and therefore heat transfer is 2 kilojoules, which we already know should be. So it's a check on the entire process, because we use this value to find enthalpy at 3. Therefore, Q must be 2. Process 3 is our isentropic expansion, and as you can see here, W external dot is found. It's an adiabatic process, so Q3 has been put to 0. And state 4 is the blowdown, process 4 going from 4 back to 1, and there is no boundary work. It's a constant volume heat rejection process, so therefore heat rejection is found here. So now that all the 4 processes have been calculated, we can go to the cycle panel, and everything else is found. Efficiency is shown here. The maximum temperature should be, maximum temperature of the cycle, net work, all the quantities that you are interested in are shown here. Only thing is that the cutoff ratio is not shown here, because this app doesn't know whether it's a diesel cycle or what kind of cycle it is. It can handle any cycle. So in the I/O panel, we calculate the cutoff ratio. As you can see, it's the ratio of the volume at 3 to volume at 2. If you go over, that's when the fuel injection is stopped, because we have reached a point from which point the process becomes an isentropic, purely isentropic expansion. So if you go through the cycle animation, you'll realize how the cutoff ratio is defined. And this is calculated in the I/O panel in this particular problem. It is found to be 2.46, where the compression ratio is, volumetric compression ratio is given 20. So now that in the I/O panel we have all these variable exposed, you can very quickly solve conduct parametric study. Suppose you say, okay, it's not 20, compression ratio is 25. How will it affect all my answers? All you have to do is to calculate, and then click the super calculate button, and all the results are updated. And you can go and see that efficiency has increased because the compression ratio has been further increased.